Thank you very much. Can you hear me?
Yeah, I can hear you. Yeah, thank you.
Okay. So let me share my screen. Okay, so can you see my screen?
Yes, I can. Yes.
Okay, so thank you, Chairperson. My name is Yohei Murakami from Ritsumeikan University in Japan. Today, I'm going to talk about language sphere, which is a current our project. And this language sphere is a socio-technical system to create bilingual dictionary for indigenous languages. Okay. So first of all, please let me introduce our history. So as you know, we have more than 7,000 languages. So this map shows the existence of the languages. So based on the statistics of Ethnologue, so this map is provided by Ethnologue, and 7,111 languages are spoken today. So we have many language barriers all over the world. So to overcome the barrier, we developed a multilingual service platform named Language Grid. And we have operated it since 2007. So it's almost more than 10 years. So our approach is not to create multilingual resources, but to connect the existing language resources to create a multilingual environment for users. So by combining the several machine translators, we can support more languages. Furthermore, by combining machine translator with domain-specific resources, we can customize our multilingual services for users' field, such as a disaster management field, education field, or medical care field. So there are many language resources are distributed, and our language grid is a platform to share these language resources as web services. And we can combine these services to support the user's field. So to this end, we introduced the concept of services into language resources. So you know the service is an interaction between user and the provider to solve a user's problem. So by shifting a perspective from language resources to language services, bilingual dictionary is not just a data. Bilingual dictionary can become word translation service. Also, parallel text become a lookup similar translation service, and machine translation provide a high-speed translation service, and even human interpreter becomes high-quality translation service. So moreover, by combining those language services, we can create a composite service with added values for users' application system. So this is a four-layered architecture for the language grid. After more than 11 years operation, 183 groups from 24 countries have joined the language grid now. And 226 services are shared on the language grid. But still, we have a limitation of the number of the supported languages because there are many low resource languages. So there are languages which has not much language resources. So we started to create language resources, especially bilingual dictionaries among low resource languages to cover more languages on the language grid. So this is the Language Sphere project. So this project firstly targeted on the languages in Indonesia because there are many ethnic groups in Indonesia and their languages are so similar and belong to the same language families. So this is a dendrogram of 100 19 languages in Indonesia, and generated by hierarchical clustering based on language similarities. So there are several language clusters. And we identified 11 clusters whose similarity is more than 50%. So, but now the Indonesia has more than 700 languages, but we select 190 languages, which have more than 100,000 speakers. And our question is, how might we create bilingual dictionaries among those dense clusters comprehensively? So first key idea is a pivot-based bilingual dictionary creations. So given two dictionaries sharing one same language, we can combine them via pivot language and extract reachable translation pairs between both sides. So for example, let's assume that we have bilingual dictionary between Malay and Indonesia and Minangkabau. Minangkabau is one of the ethnic languages in Indonesia. And in this case, Indonesian is a pivot language. Okay, so these are two bilingual dictionaries, and Indonesian is a pivot language. And we can create a bilingual dictionary between Malay and Minangkabau. But of course, the simple reachable pairs like a Kutkan and the Kiparak, the Sumpa and the Sumpa or something like that. So such a simple reachable pairs may include mistranslation caused by polysemy. In this case, Sumpa in Indonesia has several meanings. So in this case, Kutkan and Sumpa, and Kutkan and Janji, and Sumpa and Janji are mistranslations. So this research issue is how to filter those mistranslations. Therefore, we focus on the cognate words. So as you know, the cognate words are words naturally derived from the same root word in proto-language, with possible spelling difference due to subsequent phonetic development. And in this case, this is a Proto-Indo-European language, and this is a root word, and these are cognate: night in English, nuit in French, nacht in German, and nacht in Dutch. And these cognate may maintain all the meaning of the root word. So we assume that correct translation should share all the same meanings. So by regarding this assumption as a constraint, we formalize identification of correct translation pairs as weighted max set problem. Such an assumption is implemented as symmetry constraint. This means that both words have links to the same pivot words if the translation pair is correct. And in this case, this constructs the symmetric topology in the graph. So for example, in this case, the word A1 and the word C2, if they are a translation pair, they have the same meanings like B1 and B2. These are words in the pivot languages. And in this way, we can identify this kind of a symmetry topology in the graph. But the dictionaries might be incomplete and lack a lot of translations because they are ones for low resource languages, so not rich language resources. So maybe the dictionary lacks several edges. So we allow users to add possible missing edge with some cost based on joint probabilities. So we can add more edge to satisfy a symmetry constraint, and then we can select the several possible correct translation pairs. So firstly, we have to make this kind of a graph from two dictionaries. In this case, bilingual dictionary between language A and B and B and C. And then we extract all of the reachable pairs. This one, this is a candidate, but this candidate may include the mistranslations. And then based on the symmetry constraint, we selected possible correct translation pairs. And also we can add more edges and select the more correct translation pairs. And then we can go back to this phase. Based on the added edge, we can add more edges. So this is our experimental result. So we applied this constraint approach to creating a bilingual dictionary between Malay and Minangkabau via Bahasa Indonesia, Indonesian language. This shows the experimental result in first cycle. The threshold 0 means no added edges, while the maximum threshold means that we accept all added edges to satisfy symmetry constraint. In this case, the optimal threshold is the maximum. So we repeated the one more cycle. This is second cycle. So this shows the result in the second cycles. The optimal threshold is 6.0 to obtain the best F score. So this is this table shows the result. So introducing this is threshold 6.0. And this we can balance precisions and also recalls to get the highest F scores. So in this way, we can create a bilingual dictionary between a certain language pair from two dictionaries, like this, two dictionary to create a new bilingual dictionary. But to comprehensively create bilingual dictionaries, we need to extend this method to language set. Firstly, we create a hub-type network of existing bilingual dictionary among intra-cluster languages. So these languages belong to the same clusters. Based on the network, we can create more dictionaries within a cluster. And then we create a graph network among inter-cluster languages to cover all the language pairs comprehensively. But we have still two more questions. The first question is, can we have enough existing dictionaries to form this kind of the network? No, so we need at least 2 seed dictionaries. So we have to involve human to create process. And second question is, which language pair has biggest impact on other dictionary creations? In this approach, an output dictionary is used to create a new dictionary. That is, a dictionary creation depends on each other. So we have to carefully choose the order of the dictionary creations. So to solve these issues, we apply a socio-technical approach to a dictionary creation process. This process consists of 2 loops. One is the human-human loop and the human-machine loops. The first loop creates a seed dictionary here and evaluates the created dictionary. If the dictionary is correct, we can get the seed dictionaries and we can apply the previous pivot-based algorithms to create a new dictionary. But of course, this dictionary may include mistranslations. So we need to evaluate it by humans. So this is a human-machine loops. So this process enables human-machine collaborations. So it's a socio-technical systems. But to minimize the total cost, we carefully make a decision on which language pair to manually create, and also which language pair to apply the algorithm. So to solve this problem, we employed Markov decision process. This is the state transition diagram. The rectangle nodes represent the state of the dictionary creation. For example, the initial state means no dictionaries. On the other hand, the final state means 3 complete dictionaries for 3 language cases. And on the other hand, the circle nodes represent actions. Red circle means the pivot-based algorithms, and the blue circle means the manual creations. On the red parts, we create a bilingual dictionary between first step, we create a bilingual dictionary between Indonesia and Minangkabau by human. And finally, we create a bilingual dictionary between Minangkabau and Malay with pivot-based approach with successful probability of 74%. So we may have a possibility not to finish complete the bilingual dictionary by using the pivot-based approach. So this is a 74% or 26% is failures. So to find the optimal path with least cost, we employ Markov decision process and find the optimal path. And 3 years ago, we conducted the first Indonesian language sphere experiment to validate this process. So we have 3 collaborators in Indonesia to collect the native speakers who can speak Indonesian, Malay, Minangkabau, or Japanese, or Sundanese. And we can collect 34 native speakers by collaborating with collaborators. One is the University of Indonesia, the Telecom University, and the Islamic University of Riyadh. And this is the optimal workflow generated from the Markov decision process. In the first step, we created several dictionary by manual creations, and then we applied a pivot-based approach. But the final step, we regard the Malay as a pivot language, which is different from the second step. Indonesia is a pivot language, but last step, Malay is a pivot language. So pivot language is shifting. And this is a Gantt chart. So it takes 36 days to complete the whole schedules and to generate 10 bilingual dictionaries among 5 languages. And this is the experimental results. So this is the estimated cost by using our approach. And this is the real cost. So this shows we could successfully estimate the total cost of the optimal plan with just 3% errors. Also, we could reduce the 42% of the total cost compared to the manual creations to create all of the dictionary by humans. And now we created 21 bilingual dictionaries, and including at least 2,000 translation pairs. These dictionaries covers 7 languages. Okay, this is the conclusions. So our goal is to comprehensively create bilingual dictionaries among low resource languages, especially in Indonesia. And we propose 2 AI technologies for this humanities task. One is a pivot-based bilingual dictionary creations, which uses a weighted max stat. The other is a plan optimization is based on Markov decision process. Okay, that's all. Thank you very much.